Welcome to this Getting Started tutorial about Getting Started example. Have you already installed ABMT? Gotcha. Let's assume that for this moment. And when I start my projects, I usually copy the example workspace. So let's do that first. ABMT 14 examples to example workspace. So now let's start the example. Get started, start. Okay, we started right away and we look at the view. I'll make this a bit bigger. It's compiling, will be over soon. And here we go. Here we see our bouncing ball bouncing on this grid with this axis. We can adjust the view. And here we see all kind of parameters. But now let's switch to the model first. Here we have our initial height parameters, our coefficient of restitution. We can change them here. Now let's start a bit higher. Let it stop faster. Now slower. Yeah, you know how that's working. So you know better about physics than me. So here in this bouncing ball node, we look in this later. Here we have a scene and output which outputs the ball, and we composite the scene with the grid, or we add a grid and an axis, and here's the output we are watching. So now let's look in this node. This is how you create a node. You make a struct, add an annotation with node and this type auto, for example. You can add a raster. This is the interval in which this tick function, which is defined here, is called. You can add an init function. Oh no, das ist schlampig. I see the v epsilon is not initialized. Let's do this here. Yeah, the constructor will do this. So this is, yeah, it's like that. Now you know something. Yeah, okay. So anyway, yeah, here we have the ball. Here we have our outputs, our inputs. Yeah, I was talking about the inputs. These are the outputs, the scene, the position, the velocity, the energy. We see them here. So these are the variables, input and outputs, and we can use this in the tick function or in the initialization. No. Let's do this here. Because that's done here, but we come to that later. So the init function is called at the beginning. The tick function is called in the raster. So in this case, any 10 milliseconds or 0.1 seconds. The position is changed by the velocity and the acceleration, which is defined here. And then the velocity is updated. When we hit the ground, we change the sign of the velocity and multiply it by the coefficient of restitution. I've written that down. And now, then we change the output of our position. We could do this. Yeah, that's how it's done. And then we calculate the energy. So, and when the energy reaches a certain limit, then we initialize it once again with the initial height and set velocity to 0. Okie dokie. So that's how this works, and let's make some modifications that you see that how that is done and how easy it is. We take an expression. So what we do is we calculate the energy and we calculate the energy, the kinetic energy and the potential energy, and add this to a scope. So here we make potential energy, another expression for the kinetic kin. So, and kin is a half. So this is the kinetic energy, the potential energy. So yeah, let's write this out. Oh, so the height, the velocity, we add a parameter mass, which defaults to 1. Okay, let's start this once again. Go to our view, we add another scope, we take the kinetic energy, and we take schlampig, schlampig, schlampig. This is not what we wanted, so that's it. Here we see the energy, the kinetic energy when it hits the floor. The ball is fastest as it is, and then the energy is reduced. Yeah, you know what that all means better than me. So I think that's it. Thank you and bye bye.